Hello everyone, I am Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video today is going to take a look at x86 assembly language as it relates to integer multiplication, integer division, integer modulus operations. And what is I going to say? I'm using Irvine textbook. The 7th chapter is what I'm getting this information. Basically that information is being covered here when it comes to the mul, imul, div, and idiv operations. So let me bring this in a little bit. There we go. So just to say there, okay, we already know what multiplication and division is. This is 4th grade stuff. The only reason they put this stuff later on into the book is because it's a little more complicated than the addition and subtraction operations. And multiplication and division use different registers, in different parts of different registers, depending on the size of the variables, the size of the registers that you're using. So mul, just by itself, mul, is the unsigned integer multiplication. That's unsigned. So just mul by itself is unsigned. And again, it's not as easy as you might think. Some of you have tried it in previous examples, and you got points taken off because you didn't understand all the little intricacies that go with it, which is unfortunate, but that's why Chapter 7 is here and not back previous. So again, it's not the same, and there are 3 different processes, and it's just a matter of figuring out if I'm going to multiply 8-bit numbers together, 16-bit numbers together, or 32-bit numbers together. That is pretty much the only difference. And now, on top of it, instead of it being like add EAX comma EBX, which takes 2 operands, a mul operation, or imul or div or idiv, only take 1 operand, and it's presumed that part of the EAX register is going to be used as in this case, one of the 2 values that are going to be multiplied together. So you can see here, if I want to multiply a number, an 8-bit number by an 8-bit number, I'm going to get a 16-bit result. So I'm going to use AL, multiply by some 8-bit register, and get AX. And it's the same process if you want to think about base 10 math. You're like, well, what happens if I try to multiply a 1-digit number by a 1-digit number? 9 times 9. I get 81. That's a 2-digit number. Well, what if I were only trying to store 1 digit? You go, well, it's not very helpful, is it? Then it would just store the 1, and then it's like 9 times 1, 9 is 1? Like, no, that's impossible. So what we can do in the same token here is, like, we can just multiply an 8-bit number by an 8-bit number, but the result is going to be a 16-bit number. 255, which is the largest number I can store, times 255 gets me 65,535. So, and it's just the same kind of thing. Like, I need double the space just in case. And it's saying like the overflow, at least in C++ and Java, we don't necessarily get access to that in the programming language itself. We would have to do some other work to be able to get in to see the high end, the overflow portion of this multiplication. But it's just to say that it is there, sitting behind the scenes, if we're willing to go deep, go further, deeper into this, and actually start working with assembly language or down at the bytecode level. Okay, so this is just a fancy, these are just, all this is fancy stuff we'll see here in the next slides. So I say I want to multiply an 8-digit number or an 8-bit number by an 8-bit number. So I could move, just to have a different example here, into the to the AL register. I could move a 9. And then see, I can't just call mul 5. That's just not allowed. Immediate operand not allowed. For whatever reason, it's not allowed, so I have to move the value into some other register. So I'll move the 5 in here. I'm sorry, move, and then I'll call mul on the BL register. And you see basically the same stuff. Like I can call on a register mul, I can call on a variable, I just cannot call on an immediate hard-coded integer value. So then just to say, the result will be stored into EAX, and I can go ahead and call write int to see. And I'll do call CRLF just so we can get it all on one line. And what do I get out of the deal? What do we get there, right? Like, oh, shoot. Is that right? Is that wrong, right? You're like, well, I see a 45 there, but is that right? Is that wrong? So let's just test out. Let me just blow out and just replace the EAX register with 0 before I start over. And you see that, yes, everything was right in there. We were only using the AX portion. Whatever was stored in the high end of the EAX portion of the register kind of ruined. And I think we just got lucky on the 45 part, to be honest with you. Not 100% sure. But you see 9 times 5. And if you don't like it, you could try again, put an 11 in, put like a 19, and I should get 209. and I do. And so the same thing, if I flip them around, I should get 209, and I do. So I'm fairly confident that that's how you would work with a 16-bit number, or I'm sorry, an 8-bit number times an 8-bit number to get me to a 16. So AL times some 8-bit register, and the entire AX register gets filled in. And so now here, same goes when it comes to 16, or 16 times 16 gives me 32. So I could say, okay, clear out. Now I could put a 19 into AX, and 11 into BX, mul BX. So you got to, if you screw this up and you forget, you're not going to get a compiler error. It's just going to do the wrong multiplication. So if I put 190 times 11 or something like that, and I try this out, this is the only difference here. Now I get 2090 because all I did was add a multiple of 10. But what's happening here is the AX register is holding the low end of the value, but the DX value is part of the high end. So if there was an overflow, it would go into the DX region. Again, we don't see this in the high-level languages. And you go, why would we do this? And like, why is it like this? And it just comes back to just, like the way things used to be, the way the hardware, because when we only had 32-bit computers or 16-bit computers, there was no such thing as a 32-bit register. So I'd be like, it would be real easy just to put it into a 32-bit register. Well, if I create one of them, then I'm going to create 8 of them or more. And if I'm going to create 8 32-bit registers, why don't I just create a 64 then? And so you can just work yourself into this little tizzy. So the response was, well, if we need to hold 2 values, we'll just use DX and AX. That was just the way the engineering worked out, and everyone agreed to this. So AX gets the actual portion that is the actual portion that we care about. DX holds the overflow, which say, like, when we're dealing with large numbers, yes, we could care about this, but in a general use case, no, we don't. So if I wanted to, just for the sake of this, I can move 0 into EDX, and I can call, instead of calling write int, I'll call dump regs. And you can see that the EAX register holds A2A, which is whatever 2090 in hex, and the EDX register is holding a 0 because nothing got modified, nothing got larger than it. So what if I don't know, what if I multiply 300 by 354? What do I get? And so now now there is an overflow. Whatever number that is, I got 9ED8 as part of the AX register, and there was an overflow. So this means that whatever result is sitting in here, I probably could call both, right? It's called write int. After the dump regs, the answer is not 40,060 or 40,664 because the number should end in 2 zeros. So that means, of course, like I said before, there is an overflow, and this was a way to determine that happened. And the carry flag will also indicate that if I cared to. So the final example here is 32-bit times 32-bit gives me a 64-bit. It's the same exact thing. I put into EAX, I put into EBX, and now there's a 32-bit portion. The high end is in EDX. The low end 32-bit portion is put into EAX, and you really won't see much difference here except for, now the number can be fully stored in this because now it can store in 32 bits. It couldn't store in 16, but it could store in 32. And if I just modified or just worked everything up again and tried again, you could see now, well, maybe not even that. Let's see if I add another value to it, and there you go. And so now it cannot store a 32-bit value. This number is too large, so then the EDX register starts handling that overflow, and the value comes out 888. That's not right, because there should be 5 zeros to start this number if the multiplication was done correctly under the hood here. Okay, so a few more examples. So I have, okay, your turn, determine what the values of the different registers are when this occurs, when these two things occur. So let's take a look. So just pause now or whatever if you want to do it yourself before you look at the answers. So let's take a look. And so I say this is all in hex, right? So like if the AX register holds four hex digits, and then you're like, well, multiply that by 100, you're shifting everything over 2 hex digits. So the 1 and the 2 go over into the high end region, and then the AX region holds the rest, 3400. And this is all just basically hex, multiplying by 16 is the same as multiplying by 10, and just adding a 0 in our 4th grade arithmetic. And because the DX register is holding something at all, the carry flag gets set. Okay, and then so the same thing goes for this one. You like just larger 32-bit values inside of here. And instead I got a large, here's my hex, or here's my hex multiplied by a large hex number. What is the end result? I'm moving everything over 4 hex digits. It pushes the 1, 2 into the DX region. Everything else, including the 4 zeros, get put into the AX region. And again, because the DX region is holding a value, the carry flag is set. So now we have a second operation called imul, which is the exact same operation as mul, except now we're doing this to include signed mathematics. So they're really like everything else, I just throw an I in front of all this and everybody's happy when it comes to the way it is. You notice this thing is exactly the same as the other slides. It's the only huge difference, of course, is if, because I'm dealing with signed numbers, if I'm multiplying positive by positive, I should get a positive result. Positive by negative or negative by positive should get me a negative result. And then negative by negative should get me a positive result. So whatever I'm extending out into with my product, it better pass that carry along, or pass that sign bit along, the 0 or the 1. Because if I forget to do that, then the number isn't going to be in the correct negative positive format. But they say like I can just this can be just a quick little talk through, because it's like all I did basically was just go through here. I just added a little I there in a different font, and all of this is the same. It's just now we're using signed bytes, using imul, getting a signed word, using signed words, using an imul, getting a signed double word, using signed double words, using an imul, and getting a signed quad word out of the deal. That is it. All of these slides are just me adding little s's where I need to, but everything else will turn out the same. And so you got to remember, again, you have to remember, am I using signed? Am I using unsigned values? And use the appropriate multiplication. So I say, presumably for my class, the rest of my class, you're just going to be using int, which is a signed double word value. I'm not going to try, I mean, maybe I will in a few places to use shorts or bytes for things, just to kind of maybe for arrays or whatnot. But for these cases, imul is where it's at, because everything is signed when we're dealing with these numbers, and I want to make sure that the sign carries through the multiplication as it works. So there's my 8-bit, there's my 16, there's my 32. Nothing to add to this other than the fact that you just have to, again, remember what data types you're using. So now this just gets a little, like what's the only real difference here between signed and unsigned. Unsigned use the carry flag, and we'll see here that the signed value uses the overflow flag instead. So looking at this example as a my turn here, or your turn, what am I doing with this value? 8760 times 100. And so I'm looking at this number as a word, and I go, I see an 8, so I know this thing is negative because 8 or above leading digit is a 1. So I'm looking at a negative number times a positive number. So my result better be negative at the end of the day as I progress off and turn this into, what is it, AX and DX registers. So I can see, okay, so yes, I moved everything over, and it's FF. Remember, we say I'm forwarding the ones along because this has to be a negative number, and I have to keep extending that out. So FF876000. And again, and just like before, just a little different here is because I'm using the DX register at all, I have to set the overflow flag to indicate that this number cannot be stored as a 16-bit quantity. So let's see. Let's try again here. Let's just see what happens. I move AX and BX, 8760 hex, and 100 hex, multiply, do an imul with BX, call dump regs, call this, call that, and what do I get? So let's see. So I get FF87 here in the DX. Remember, it's the low end. That's all I care about. And then here in the BX, I get, I'm sorry, AX, I get 6000, like I'm expecting to. And then the overflow flag is set because there's junk inside the EDX register. And that's all there is to that. I mean, it really is. So let's move on to division. Okay, division is exactly what you would expect division to be. It's a numerator, it's a denominator, it's A divided by B. And this is, remember, this is integer division, so the whole, we have a whole number, and we do have a remainder. And so what's interesting about this is a division operation of any kind, div or idiv, as we'll see, will give both the quotient and the remainder the AX register or of some sort of, you'll see here, the quotient is held in these types of the registers, and the remainder are held here. So it's interesting because you do you do a division and you do a mod in C++, and you go to disassemble the code, and you'll see it actually called div twice, and it doesn't have to be that way. The program is that naive. It doesn't look ahead. It doesn't think, oh, what's going to happen in the next line of code. But if we were thinking ahead, we could save that division, because division is a very, very slow operation. It's basically the slowest operation that we can perform. It's an individual operation. So of course, unsigned is the div, and it's again not as easy as you think. And there's 3 versions of this. And again, let's just take a look at the versions individually here. So a difference between 8-bit times an 8-bit got me a 16-bit. And now the reverse of this is I actually have to have a 16-bit number divided by an 8-bit number to get an 8-bit number. So this is saying this is the lowest, this is the smallest one we can use. AX, the 16-bit quantity, has to be divided by an 8-bit. And so those 16 bits get broken up to 8 bits for the quotient, the whole number, 8 bits for the remainder. So I can go ahead and, let's see, just like they kind of have here, I'll move into AX, or just to show you slightly different here since I haven't done it yet, I will set up a variable called A, and I'll make it a word, and I'll say it's a 5, and I'll say B, I'll make it 15, and I'll say this is a word, this is 4. So I'm moving A into AX, all right, as a word. I'm sorry, and then we'll just make this easy on myself and make this a byte. Sorry, word divided by byte, right? Because A is a word, and now I can move into the BL register. Because again, I cannot just do it. I just can't do a div with 4. That will not work. Immediate operand not allowed. So I'll move into BL the 4, and then I'll do a div or a bib or whatever you want to call it. I'll do a div BL, and so what do I get out of this? I should get 3 remainder 3. Because so let me use a different number just because that doesn't. How would we know if it's not just printing the same thing twice? So I can say, oh, okay, 17 remainder 4, or 17 divided by 4 is 4 remainder 1. So if I do my call dump regs, I don't have to do my call write int anymore. And so what do I get out of the deal? And so now that it's always tricky, right? You're looking at these, you're like, what am I looking at? And I go, well, the EDX register, it doesn't matter at all. The AL and the AH is all I'm looking at. So what was I saying? The high end is the remainder, the low end is the quotient. So these 2 bits right here, these 2 hex digits, 0, 4, that's my 4, because that's the AL register that's holding the quotient, which is 4. And the remainder is these 2 guys right here, the AH port, that's 0, 1. So 4 remainder 1. So AL and AH hold the result of that. All right, so moving on to the next one. We have a 32-bit quantity that's divided by a 16-bit quantity, and the result will be 16 bits set aside for the quotient and 16 set aside for the remainder. So just to change things up, I'm going to use, I'm going to have to use word and word here. So I've got 94 and 11, and I'm saying I'm using word because you say I have to fill in the DX register with the high end of the number that I'm going to be dividing, and because so this is going to be, DX is a word, and A, which is AX, is a word. So 94 gets split into this 32-bit quantity, and it's just weird because you think, why not just use the AX? And that's just, again, backwards compatibility and the way things used to be, and we just never changed it. So 0 goes into the DX register to fill in that, because if you forget, you're not going to get the correct result when you go to do your division, because it's going to be a hugely large number, because there's just going to be garbage in those bits. So DX is 0, AX gets A, so then DX colon AX gets 0 colon A, and then I'm dividing by B, but I have to move the value in. I can't just, actually in this case, I can just do div B. I can't div by a hard-coded number. I can do memory, I can do variable, and I can do register, but I cannot do immediate value. So then 94 divided by 11 should get me 8 remainder 6. And so you can see the AX portion is 0008, which is the 8, and the DX portion is 0006 is what I'm expecting to see, just like you see here. And so I'm very happy with that result. And so now the final here, taking a 64-bit value, dividing by a 32, and getting a 32-bit remainder. So just jumping this up one time over to get the exact same result, just in a larger space here. I could say, okay, EDX is 0, the entire EDX register is 0, the entire EAX register is equal to A, and then divide by B. And I get the same result. I just get it now. It's in the entire EAX register holds the result of the quotient, and the entire EDX register holds the result of the division. That's pretty much all there is to it. And say there's a different example for each of those. I wanted to keep it a little different because so you guys have two examples to look at. Okay, so more your turn stuff. Using hex code gets a little more complicated. So what if I actually crammed some stuff into the DX register? 87 goes in there, and then 6000 goes into AX. So this number is larger than a 32-bit quantity, something that we could not do in C++ or Java. So we could take a large number and try to divide it by 100 hex, and then divide it by this BX value. What do we get? And so we'll see what we get in a moment. Same thing goes here. By 87 6002 hex divided by 10, that one might have a little problem. Let's take a look why. So let's look at the one that isn't screaming a wall of text at me first. So if I take 876000 and shift everything over 2 times, these 2 digits are the remainder, right? If you just put a dot right there, say .00, so excuse me, the DX register will hold a 0. But as when it comes to everything else, 8760 shifted over twice, so DX will hold 0 because that's the remainder, but 8760 is the result. And so now this is where things get tricky, and it's like I'm not 100% sure how the compiler or can do this without crashing your computer, but if you put this code in, it will actually come up with an exception. And now it won't, right? Because I'm trying to do it. But let's see, if I put this code in here and I run this, there it goes. I actually have an unhandled exception integer overflow. And like, why? What the heck is going on? You're like, well, what's happening is I'm trying to take a large number like 876002 hex divided by 10 hex. And so what happens is part of the number of the result of the quotient, the number's too big to be stored in the storage that we set aside for it. And because of that, part of it gets blown out when we try to fill in, because the AX register and the DX register are the 2 registers that are played with, but the DX holds part of the quotient, but now it's blown out by the remainder. So you're not going to get the correct response out of this. You're not getting the correct answer. So it's just going to throw up on you. And I say, I think we don't ever see this is because we never fill in that the high end. We never do this in real code. We always use 32-bit values. So we've kind of minimized the damage, and we never can. We've basically made it so that you can't accidentally crash your whole program with one division. Because like I said, all I'm trying to do, what if I just divided this number by 1? And you go, nope, not going to work. Like, your whole program shouldn't crash because of that one little mistake. So that's what's going on there when it comes to this. You just have to watch out for that, and hopefully you'll never see this because we're going to fill in everything with zeros as we go. Okay, so now idiv. So div again was unsigned, so then idiv is signed. So this is the one where things get a little tricky. So say everything we did with unsigned didn't require any of this extra stuff we're going to be doing here in a minute. But as you can imagine here, if I'm going to extend, right, the whole point is, just like before, I had to use the DX register, and I just threw a 0 in there because I'm dealing with unsigned values. So I'm just zeroing it out, everything, and keeping it positive. But in these cases, when I'm doing signed integer division, I have to make sure that I take the sign bit and I extend that out so that I keep the number exactly the same, positive or negative. So if it's a positive number, the 0 gets extended. If the value is negative, the ones get extended. So, but they use the exact same syntax, just like mul used the same between mul and imul. You get the same stuff here between div and idiv. And so now here's the tricky part. Like before, we could just do move dx comma 0, right? But now, like, imagine how much work would go into that, having to look at the doing an AND operation or a test operation to figure out what that one bit is. Is it a sign? Is it an unsigned? Then fill in the DX region. Like, that's a lot of code to write every single time I just want to do one division. So there are 3 commands here that allow me to fill in this stuff with the correct value without having to write all those if statements and all that code. And And it seems terrible until you read it out. Convert byte to word, convert word to double word, convert double word to quad word. And so it knows back here, where's my, here we go, with this kind of, with this here, it knows to fill in the high end. So if I had AL, it would know, I'm sorry, AL, it would know to fill in AH. If I start with AX, it knows to fill in DX. If I start with EAX, it knows to fill in EDX with either all zeros or all ones, depending on the operation. So, and it's just a matter of, am I dealing with bytes, words, or double words? And so it fills in what it needs to fill in so that you can do the math correctly. So let's see, the previous slide shows examples of CBW because I'm converting a byte into a word. C, convert, B, byte, W, word. Convert, byte, word, C, B, W. Okay, so then something like this here, just to go through this, and everything is signed again, so you have to worry about signed stuff, signed word, signed byte. IDiv gets you signed byte results. And you can't really, it won't be very simple to see this as a bunch of dump regs, but just to see what you see, right? So move AL, comma, -48, and then so CBW to convert that byte into the double word, take that AL and extend it into the AH region, move into the BL register of 5, and then IDiv BL. And what do we get? Oops, sorry, hold on. Let me get rid of all this other stuff. What do we get? So this is the fun part here. We get -9, remainder -3. So this is where you got to remember your hex and your negative hex. F7, oh boy, what is that? That is actually -9. And then coming back to D here, I'm sorry, F7, I keep forgetting. Whoever uses 8-bit, I don't. F7 for the quotient. FD, which is, that's my -3. So FF, FE, FD. So it's, -9, remainder -3. And it's like, you can actually have negative remainders, you just got to remember that. So the math is right, we just got to understand that, the correct registers are getting placed with the results of the math, what we're trying to perform. So moving on up, so the same thing goes as before. If I wanted to convert this, and just instead of AL, I use AX. And so if I CBW, that won't work out now because I'm using a word and I need to convert that into a double word so that I can do the same math and I get the same result again. Now things are a little more different because FFF7, that is AX, that holds the result. So AX is holding the -9, whatever I said earlier. And then now FFFD, the whole DX register holds the remainder, which is my -3. Okay, so that's that. And then to finish up the deal here, I have myself the 64-bit version where I say, okay, EAX, put the -48 in here. So now this is a double word that needs to be converted into a quad word because the 32 bits on the right-hand side need to get moved over. The signed bit anyway needs to get moved over into the EDX region. And so I have to divide by 32-bit region. And again, the same results, but now again, the entire EAX register is now used, FFFFFF7, and that is my -9, and then my FFFFFFD, the entire EDX register holds the -3 value. So our final year turn before we move on to other things related to multiplication and division. So what have I got here? What is the result here if I put FDFF into the AX register? And so that's a word, and convert that into double words, so CWD. I do a move, and I put 100 hex into this thing, and that is actually 100 hex is 256. So I do an IDiv, and so I get -513 divided by 256. So if I do this right, I should get -2, remainder -1. It's hard, like for me, like mathematically speaking, I don't think they have negative remainders, but the math in computer science, the math on a silicon chip does. So, and it's one of those, you can run it out. Well, can I steal the code and just run it and just see what happens? And so what do I get? So the AX and the DX registers, FFFE, that's my -2, right? FFFE, and FFFF is my remainder, -1. because it's 2 times 256 is 512, and then one more gets me to 513. There can be negative remainders. It's funny stuff about that. It ruins my day half the time when it comes to video game stuff. Wish there was just one mod that did it all. And just, if I told you a positive 3, it would give me a mod between 0 and 2. But oh well, I'll get off my soapbox, and let's move on to other parts of this, the final parts of this video. Tying everything together, everything we've learned. So I say, well, I've already kind of halfway described it before. If you disassemble a lot of the code you write in C++ at least, you will see that the computer, at least with the optimizations by default that come with Visual Studio, it just brute forces it. It doesn't do any thought process to try to condense down, or it just kind of just literally translates into assembly language. So again, if as a human, if you could convert that down and reduce down the algebra or whatever you need to do, you will speed up your program because the compiler doesn't know any better. It just doesn't. So for things like this here, this problem here, let's be the compiler for a few examples before we call it a day on this video. So I say, okay, so var1 equals var1 plus var2 times var3. And I go, well, first question is this signed or unsigned math? And one way or another, we'd have to be told. Because outside of this, there's no way to know that this is going to be a positive or a negative, because addition and multiplication, there's no specialness to it. Like mul versus imul, we don't, we need to be told. We need to be, like addition doesn't need to worry, but multiplication does, so we'd have to be told. And so if we were told, or we found out one way or another that it was unsigned, we use a mul, and if we find out we're using a signed, we're using an imul, because there's no such thing as add versus I add, it's just add. The math turns out exactly the same. So in these cases, I'm putting var1 into EAX, I'm adding the var2 to it, so the EAX register then can get multiplied by var3, and then the EAX register gets moved to var4 because now the result gets put in there. And if there was overflow, remember, EDX register would hold it, but according to the way C++ works and all that, we just silently let that fail. And again, it just works, it's exactly the same code, one character difference between the mul and the imul here. So next problem. It's not as easy. When you stare at this thing, EAX equals negative var1 times var2, quantity plus var3, and you go, is this signed or unsigned? And you can't look at this and go, oh, this is unsigned math because of that negative sign. Like the negative sign in this indicates to me that it's got to be signed math, because there's no such thing as a negative signed or negative unsigned value. It goes from 2 to positive infinity. There's no negative part of that at all. So I just put the little x there to go, nope, in this case, there is no unsigned value. So what do I do? Same, I'm taking var1 and moving it into EAX, and I'm negating that. So remember, also, this is a big deal, your job is not to change any of the other variables. Your job is to only modify the EAX register at the end of the day. So if I just went ahead and said neg var1, I've modified a variable. I'll get the right answer, but then I've modified a variable, so everything else will just fall apart later on because I'm not supposed to do that. So move so the register is fair game. var1 EAX move, negate that, then I can do my imul, and then I can add var3 to get myself to where I need to go. And because EAX holds the result of the multiplication, I just got to add var3 to that, so it doesn't need all that extra work. Okay, so a couple more here, or another one here. This one's just a little more complicated. var1 times 5 divided by var2 minus 3. And this one, I don't see any negative signs, so I have to be told if it's unsigned or signed. And again, the only true difference is it's mul versus imul, div versus idiv. But in this case, what are we doing? Because we got to store 2 values to make this thing work. We got to keep the numerator here and the denominator, so the numerator better be EAX, and then the denominator can be anything else. So var1 gets EAX, I move 5 into EBX so I can multiply it. So at this point, EAX holds the value as I'm expecting for this whole quantity. And then I can take var2, move it into EBX, because I don't need it anymore, because it's like I'm already done with this portion. So var2 can get EBX, put in EBX, subtract 3 off, and so now EAX still holds the high end of this, the numerator. EBX holds the denominator. So let's do the division, and then the result will be stored in EAX, and then I can move that to var4. So that's the whole thought process to make this thing work. So one other little detail that almost caught me off guard here, and I actually stopped my video to take a look at this because I completely blanked on this, was like, well, if I have an IDIV, I've told you that you have to have one of those CBW or CWD or CDQs, but in these cases I don't, because when I was doing this and I did the multiplication, because I did the multiplication, EAX gets stored with some of the result and EDX gets stored with some of the result. It's stored together. So the EDX register is taken care of for me by the multiplication, so I don't have to go ahead and fill in that extra space because it's already been done by the multiplication. So that's why you don't see that. You've seen that in previous examples when I'm trying to do just a straight up division, but in this case, the variable, the multiplication that came before it will handle everything appropriately. So just so you know. So now moving on to the final example, it's the same deal, and I just have to get rid of this. This is a typo. So let me just put this here. And so what have I got here? So I have, what am I doing? So this time around, I'm actually doing the math differently here. I'm doing the denominator side first. And so what is this? This is the modulus operator. This means instead of taking the EAX portion of the result, I'm taking the EDX portion of the result. So I'm saying, okay, move var2 into EAX, do a CDQ. So I'm doing a division first without any multiplications or anything. So I do need that CDQ there. And then I can do an IDIV with var3. But again, I need to keep the EDX register, and that's where I'm going to put it into EBX, because the mul here is going to blow out EDX in a moment anyway. So I'm going to move it over into EBX so I can use it in a moment. So then now this side is taken care of. That's EBX. So I can move -5 into EAX. I don't have to worry, since I'm doing a mul, I do not have to worry about using EDX or anything like that. I can do imul var1, since that will just presume that is an integer-sized thing. EAX will store the result. So then now, and then EDX will also hold the result. Remember, this imul will handle everything. It'll fill in the EDX portion. So EDX and EAX is taken care of. So now I can come back and use that EBX that I saved from previous, do my IDIV, and then the result will be stored in the entire EAX register. Move that to var4. So it's complicated. It seems like it's division. It seems like it's multiplication. Multiplication is easier than division, of course, because it's a CDQ thing. When do I use it? When do I don't? Because if you don't use it when you're supposed to, you get large numbers. And if you use it when you're not supposed to, you can kind of blow out things the other way around. So it's like, don't do it too much and don't do it too little, and it should turn out just fine for you. Okay, so last examples here for the day. So let's take a look at, let's see, EAX equals EBX times 20 divided by ECX. EAX equals ECX times EDX divided by EAX. And then one of these kind of guys, var3 equals var1 times -var2 divided by var3 minus EBX. Okay. So, oh yeah, and it also says presumed signed values for all of these. So we're just going to go down and use the IDIV and the imul for everything. Hopefully there's no typo there, which everything looks good so far. So, okay, so you don't even need necessarily the parentheses for this because multiplication and division are at the same PEMDAS level. So it's EBX times 20 divided by ECX. So I move a 20 into EAX, I do my imul, and then that fills in everything. It fills in EAX and fills in EDX. I can do my IDIV with ECX, and so the EAX register holds the result, so I don't have to do a move. And so there's no move at the end here to take care of anything like that. And so 3 lines of code get me to where I need to go. Fair enough. Okay, so now this is a little trickier. Let me see if I can, let me pull up an Excel worksheet real fast just to see what the heck is going on. Okay, so let's just, what do we have going on here? We have all these different values, and I have a stack and all sorts of stuff. Let's see. Holy moly, right? So let's just put a value to things here. We need EAX. Let's see, I don't know. Let's see, EAX is 10, ECX is 22, and EDX is 13. I don't know. I'm just making up numbers, and I'm sick of using 1s, 2s, and 3s because it always bites me in the butt. So I'm going to right justify this so we can see things here. So what are we doing? This code. So what should the end result be? Let's see. It should be equal to ECX times EDX divided by ECX. Cut off the remainder. So we should get 28.6 out of the deal. So we're just keeping track of the whole number part. So we should get 28 when this is all said and done. So what am I doing? I'm pushing EDX onto the stack. That's a 13. I'm pushing EAX onto the stack. That's a 10. I'm taking whatever's in ECX and I'm moving it into EAX, putting the 22 there. I'm doing an IMUL between this and EDX. 22 times 13 is 286. And so 286 will go into EAX, 0 will go into EDX. And now what I can do is I can pop off EBX value. Okay, so take this here and put it into EBX. All right, EBX, put the 10 in there. Do an IDiv with this. So IDiv 286 divided by 10 gets me, just like before, it gets me 28, and it gets me the remainder 6. And then I'm going to pop back this value into EDX, 13. So what have I got? EAX holds the result. ECX and EDX were put back to the values that they were when everything started. So again, this is just kind of getting a little trickier. You don't necessarily think all the time you have to have all these pushes and pops just to do something like this. But if this was in a function, you definitely would need to worry about that kind of stuff. And then, so yeah, so we're all good there. And so everything's cleaned up, and the 28, just like we expected, is sitting here in the EAX register. Okay, so final result here. How do we handle this guy? var1 times negative var2 divided by var3 minus EBX. So this one definitely would have to be a signed value no matter what. And that's because I'm staring at a negative. Everything else, otherwise it would have to be told, and I am, that it's signed. So what are we doing? We're doing the left-hand side first. So I'm moving var1 into EAX, and then I'm moving var2 into EDX, negating it, and then multiplying it, right? So var1 times negative var2, right? That's what I'm dealing with. EAX holds the quotient, which is the whole number part of the multiplication, which is what we're going to need for the INdiv in a moment. So then what do we do? And I could have put it anywhere, but I put var3 into ECX, and I subtracted off from ECX EBX, because that's what this does. So now EAX is holding this part over here. ECX is holding this part over here. I do an IDiv. And so the EAX register will hold the integer result of this, which then gets put into var3 to finish the job. So it's 7-8 lines of code to get the job done, but it is pretty complicated because there's there's a lot of operations going on here, and we have to make sure they go in the right order, and we have to make sure we end up with the correct result, because obviously that is the most important thing over efficiency, is getting the exact correct result that we're expecting to see. All right, so that covers pretty much everything in this lecture slide show. So if you have any questions, swardb@cod.edu is my email address. Otherwise, hit me a comment here on the old YouTube. And thanks for sticking it out, and we'll see you next time.